Cool. Okay. Nice. Yay. Yes. So, yeah, let's get going today then. So our topic for this last lecture here, last contentful lecture, is identity. And in particular, the kind of plan for today, I want to start by introducing you to the kind of a series of questions we might ask about the nature of identity. And in particular, a very specific sense of identity that we're interested in when we're thinking about things like formal logic. So that'll be the first section. And this will really be mostly ground clearing. I'll give you a few definitions along the way, some distinctions, but really kind of motivating it. And then the core of what I want to do and what I hope we'll be able to talk about today is basically the relationship between this special sense of identity and two other notions. So first, it's going to be on identity and indiscernibility. So this is what the paper we read for this class was, Black's paper on kind of a bunch of spheres. It's a weird kind of dialogue thing, right? So Black is really concerned with this identity and indiscernibility. So more exactly on what indiscernibility is in just a few minutes. That's the first thing I want to talk about. And then the second one is identity and necessity. So in particular, if you remember from, I think 4 or 5 weeks ago now, we talked about this notion of possible worlds. We talked about this sort of idea that certain claims might be necessarily true. They must be true. Well, one thing you might wonder then is, what's the kind of modal status of identity claims? Are they contingent? Are they necessary? Are they necessarily true if they have a truth value at all? So what we might call weak necessity. We'll talk about that in a few minutes. That's what I want to talk about in the last section. And in particular, I want to kind of build to a case that seems to challenge a very intuitive idea that identity claims are necessary if true. So that's the kind of plan. So let's get started. So, as I said, the kind of beginning section here, I want to familiarize you with a very specific sense of identity. And really here, the link back goes very nicely to the stuff we were doing when we introduced first-order logic. Right? So one strange element of FOL was the identity predicate. And it was strange in a whole bunch of different ways. So one of them was just kind of syntactically or grammatically, it was the only one that we wrote in the middle, right? All of the other ones, you put the relational predicate first. This one was one where you flank it with names or variables. Another kind of more interesting special thing about the identity predicate was it was always one that we never fixed the extension of. Even when we were building interpretations, we wouldn't give the extension of identity. We might talk about, oh, there's the extension of the relational predicate L or the relational predicate R, but identity wasn't like that, right? We just took it. It was given. And we said when we were talking about it, I know this was a long time ago now, but when we were introducing it, we said that identity holds when objects were the very same thing. And one of the things we're going to try and do is make more sense of what we mean by the very same thing. And notably, we didn't talk about proof theory or natural deduction, but it's notable that identity also has its own special proof theoretic rules. In fact, it's the only predicate in FOL that lets us literally produce a sentence from nothing at all. Because according to most proof theoretic approaches to first order logic, you can generate this sentence from literally nothing. That is, you can have an identity claim with the same name on both sides, and it's guaranteed to be true. And in fact, we have a kind of reasoning behind it already. So if you go back and remember, when we were talking about FOL, we said there can never be any empty names. This we talked a little bit about last week, right? How that could lead to some difficulties with things like negative existentials, empty terms. But if we know that there can be no empty names, then we know that this sentence must be a logical truth. Because whenever you use the name, it picks something out. And of course, if you just use the same name twice, you're basically just saying this object is the very same object as itself. That's weird. That's weird. Because we just bootstrapped something into existence, effectively. So all of this is kind of getting at the idea that the identity predicate's weird, and whatever the identity predicate is supposed to express is also very weird. In particular, there's a whole slew of philosophical problems that seem to be about identity. And what I hope to do today is to help us understand this sense of identity and think about some of the associated puzzles. In order to kind of get going, it's useful to make some distinctions. So the first distinction I want to make is the difference between identity and what we'll call individuation. Have people come across that term before? Individuation? You see, you're shaking your head, but technically I did give you a principle of individuation, right? Does anybody remember the thing that I gave you that was a principle of individuation? It was the axiom of extensionality, right? It told you when two sets are identical. It also implicitly tells you when two sets are distinct, right? So individuation is the act of deciding or determining when two things are or are not identical. And identity is the relation that the things either stand in or don't stand in. So individuation is something we could kind of do. It might be epistemic. It might be metaphysical, depending on how we want to think about it. Whereas identity is just, it's a relation that either holds or isn't.
Individuation is subscriptive, or what do you mean?
So it's not necessarily, I'm not quite sure what you mean by subscriptive.
Because you describe two things, as I'm reading here, you're telling that two things are identical.
Yeah, no, telling is in determining, settling, right? Not literally kind of asserting, right? Determining whether two things are identical or not, right? So again, if we think of like the axiom of extensionality, it tells us, hey, how can you settle whether two sets are the same or not? Well, look and see what their members are. If they have the exact same members, they're the same set. Yeah.
How is identity different from individuation?
Good. So individuation, again, is something that we might use or might go through. It's a process. It's an act of deciding or determining whether the identity relation holds or not. And then the identity relation is just the relation. So individuation is a process, something like that maybe, and identity is the product.
So they're not actually like opposites?
No, not at all. Not at all. But it's just important that we keep the two different things clear. Right? So the axiom of extensionality, again, gives us a way to individuate sets. It tells us when they are or are not identical. Now, when we think about identity, right, not individuation, but the very notion, the relation, in fact, there's a bunch of different ways you can think about identity. Our first one, a difference here, is what we might think of as qualitative versus numerical. So qualitative identity is literally just sharing the same properties. So qualitative identity is just being maximally similar, or as maximally similar as you can get. In contrast with numerical identity is the relation something bears to itself and literally nothing else at all. So qualitative similarity qualitative identity is similarity turned up to the maximum degree. Right? Numerical identity is literally how many are there. To give an example here, think about the sort of type token stuff that we did before. So we have how many letters are here? Well, one answer is there's 2, one answer is there's 3. The motivation for saying that there's 2 is that these 2 are qualitatively identical, or at least sufficiently qualitatively identical. But they're numerically distinct. There's 2 of them. There's 2 letter A's. Numerical is literally count. Qualitative is tell me what it's like. Does the difference here kind of make sense? Yeah.
So what you have read is numerically, like it has what you have written hasn't the same qualitative and numerical value. Like it's different in those.
Yeah, right. So these 2 tokens are, again, setting aside my terrible handwriting, they're qualitatively identical, but they're numerically distinct because there are 2. Often when we're thinking about identity, and in fact, when we think about what's expressed by the equal sign in FOL, it is numerical identity. It is not necessarily qualitative. The second kind of distinction or way we might think about identity is at or over times. Yeah.
Would it only work with the numerical, or would it only work in sets?
It works generally, right? So if you have a twin brother, you might be qualitatively identical in many, many ways, but you're still numerically distinct because there's 2 of you. So it doesn't have to be in terms of sets. It's just literally a numerical identity is how many of them are there. Qualitative is what are they like. So our second one, again, we can think about synchronic or diachronic. These are really fancy terms. Synchronic just means at a time. So we can ask about identity at a time. Is this thing identical to this same thing at this time? And diachronic means over time, across time. So for example, I'm identical to the person I will be in a week's time. Similarly, I'm identical to the person I was when I was 3, at least numerically. But it seems very clear that qualitatively I'm very different than I was when I was 3 years old. So there's a sense in which I stand in the diachronic numerical identity, but I do not stand in diachronic qualitative identity. We have different properties, the me at 3 versus the me now, but we are the same person. Again, synchronic, we're just sort of freezing the world and asking, okay, individuate here, now. Diachronic, we're looking at a bunch of things across time and asking, hey, can you track this object? Yeah.
Well, with synchronic identity, is it that you always talk about 2 things?
So actually, one of the weird things here, when we're talking about numerical identity, is of course, no, we're not talking about 2 things. Because if they're numerically identical, there's only one thing there anyway. What you might...
Yeah, but you have 2 A's, right?
Yeah, that's why they're not numerically identical. Because there's 2 of them.
Yeah, but with synchronic identity at the time, if you look at those 2 A's, then it's never the same.
Good. So this is the reason to say that they are numerically distinct. They are not numerically identical. Right? So the best thing you can kind of think about, right? Synchronic identity. Suppose that you have like a football example. You're watching a football game and they take a snapshot from like 3 different angles all at the same time. You could then identify a particular person in all 3 shots from the different angles. This would be a kind of synchronic identity, right? From the side, okay, there's Messi, there's Messi, there's Messi. All of them are pictures of Messi. It's him from different angles. That'd be a kind of instance. Or you might talk about, hey, here he is when he was a little kid, and here he is now running around in Miami. That kind of thing. Yeah.
For what purposes do you use the synchronic and the diachronic?
Good. So diachronic is often interested in things like persistence. Right? Here's a famous debate you will have undoubtedly heard. Does everyone know the ship of Theseus? Right. A jokey version of it. Forgive me, Helen, I'm a different ship. Are you though? Right. The unjoke version. Theseus has a ship. Every day he takes out a plank and replaces it with a new one. After 100 days, he has replaced every plank. Is it still the same ship? We can complicate the case further by saying as he replaces it, he uses the old planks to build a new ship. So at the end of 100 days, he's got a ship over here made up of new planks and a ship over here made up of the old planks repurposed. Which one is his first ship? Oh, shit, that's the kind of diachronic question, right? So diachronic identity is about persistence and identifying across time.
Yes, with the same like that they say that in 7 years all your atoms are changed, and that are you a new person or are you still? Yeah.
Right. So again, diachronic identity is often about this kind of persistence cases. Synchronic identity is much more about, hey, I've got a bunch of things, but how many of them do I actually have? Is this just the same object being displayed in different angles, or is this in fact two different things? And this is just a jokey highlight, but problems about numerical identity, either in the synchronic or diachronic form, they're core debates in philosophy. They've been going on for forever, basically. I mean, there's a reason this is called the ship of Theseus. It's not because current metaphysicians pulled it out, right? This was a debate that they were having in Homer. Joking. So there's a bunch of debates and questions philosophically that have to do with notions of identity. Please.
On part of the synchronic identity and the diachronic identity, could you say that there are any set answers to any question?
Yeah, right? So what you might think is that one of the philosophically interesting things here is to come up with principles that answer these questions. So you might think, when you're thinking about this ship of Theseus puzzle, that the challenge is come up with an answer to the puzzle that tells us diachronic identity conditions for ships. And you might think there's no good answer here. That's a view. That's something we'll come back to when we think about identity and its modal strength. But it seems at least there's possible answers that we could float.
I don't really get the messy example with the camera.
Ah, good. So again, when we're thinking about synchronic, what we can basically ask is, right, I've got some data that represents the world in one way, I've got some data that represents the world in another way, and then I wonder, hey, these kind of things depicted in my data, are they the same object or are they in fact different objects? So that's a kind of instance where I'm not interested in across time. I'm not, hey, is this thing persisting? But is this literally the same as that at a time?
And then messy would be like constantly the same. Messy, constantly you have different angles.
So the idea is basically we have different viewing angles, but it's all different viewing angles for the exact same individual.
So quantitatively, you would say the angle of the quantity is the same. So
Well, this is why we want to, in this case, what you're doing is you're sliding properties about what the viewers are seeing into the object. But the angle that you have isn't really a property of Messi's. That's a property about your relationship to him. So this is going to come back when we think about our first puzzle, about indiscernibility and identity. We'll come back to it. Yeah, do you have a question? No, I guess not. Okay. So, now weirdly, one of the things that's philosophically puzzling about questions about identity is why identity is at all puzzling? To kind of get the idea why this is a bit funny. So most of these puzzles about like the ship of Theseus don't really seem to be about identity per se. It's about something like shiphood. Like, what are the essential properties for being a particular ship? What changes can it survive? Or you mentioned the one about like, oh, we replace ourselves over X number of years. Do we survive that? And we can phrase that in terms of identity, but it seems more about something like survival, something like persistence. So we can understand these maybe as problems about change, or as about person or shiphood, or about persistence. But of course, we can still understand these as very related to questions of, in this case, diachronic identity. Yes?
It's a question not about identity, but about essence, for example, like which is the essence of ship and essence of a table.
Yeah. I mean, but of course, note that the answers to those will then pay out in terms of claims about identity or non-identity. If it turns out that the essence of a ship is such that it does not survive complete replacement of all planks, then you now have a principle of individuation for ships. And you have an answer, to come back to the point earlier, you have an answer to numerical identity questions for ships. Is this the same as that one? Well, do they have shared planks? No, then they're not identical. You've got two different ships. Bang. So you get answers to identity questions, but the identity question is not the source of the puzzle. The puzzle turns out to be about these other things. That's the usual reply. That being said, there are some legitimate problems specifically with the nature of identity itself. So let's turn to our first one. Sorry. Got one slide ahead of myself. So one thing to note is this kind of, hey, there's no problem with identity. This is often called the classical view of numerical identity. The view here basically says, hey, numerical identity is the relation everything has to itself and nothing else. Notably, this isn't very useful because nothing else just means everything that's not numerically identical to it. So this is basically saying it's the relation that a numerically identical thing stands to all numerically identical things. Not very useful. It is an equivalence relation, so it's reflexive, symmetric, transitive. But the big one, and this is the interesting one, is the classical notion of numerical identity obeys the indiscernibility of identicals. So I'm going to apologize now because I'm going to give you two principles. One of them is the indiscernibility of identicals, and the other is the identity of indiscernibles. I know, I hate it, but it is what it is. The first one, the indiscernibility of identicals, tells us if two things are identical, then they share all their properties. If you literally have the same thing, then it has all of its properties in common. We have used this principle already. When did we use this? Do we remember?
Nominalism?
That's a version, but we used it in an argument last week.
Last week I wasn't here, but this is Leibniz's law.
This is a version of Leibniz's law. So Leibniz's law is weird because it gets used for a bunch of different principles. But yes, this is sometimes called that, yeah. We use this for the problem of substitution. Remember the puzzle about Lois believes that Kent is a reporter? Lois believes Superman is a reporter? If Kent is Superman, then Superman and Kent have all their properties in common. So if Kent's a reporter, so is Superman, because they're the same damn thing. So the indiscernibility of identicals tells us if two things are identical, then they are indiscernible. They have all of the same properties. Yeah? And that's really plausible. Because if two things, are identical, well then you just got the same name. Right? You've got the same thing, two different names. So, right, oh, this thing's a reporter. Well, cool, then this thing's a reporter. Doesn't matter what you call him. So numerical identity obeys this principle. And this is cool, right? This gives us a connection between numerical identity and what properties an object has. But what about if we flip the direction of the conditional around? So this one says, if two things are identical, then they have all the same properties in common. What about the other way? So the other way around, again, unhelpful, apologies already for the name. The other way around is the identity of indiscernibles. I know, I said already, it's bad. Don't blame the messenger, right? So the identity of indiscernibles says, hey, if two things have all the same properties, then they must be identical. Hey, this thing's a reporter that can fly, works the Daily Planet, loves Lois Lane. Hey, this thing's a reporter that can fly, works at the Daily Planet, loves Lois Lane. Oh, these obviously must be the same object. If indiscernible, then identical. That's what this one says. And there's a good reason to want this principle to be true. And the reason to want this principle to be true is it gives us a way to answer questions about numerical identity. It gives us a principle that can solve questions about, is this the same thing as that? It will characterize or cash out numerical identity in terms of similarity, sharing of properties. According to this principle, maximum similarity entails identity.
I don't get it. What's the difference between indiscernibility of identicals and identity of indiscernibles? What's the difference?
Good. So let's look at the two conditionals, right? We'll go back a slide. Here's our first one. It says, if two things are identical, then they are indiscernible. They have all their properties in common. If identical, then share all properties, maximally similar. That's our first one. Nobody doubts this one. The one that's debatable is if all properties are shared, then identity.
But what's the difference between that?
Think about how you would express them. Look at the if-then. What's the antecedent to this one? What's the antecedent here? Right? What's the antecedent for this one? It's the conditional in different directions. This one says, right, if identical, then they share every property.
Yeah.
Is this how we would express our next principle, the one on the next slide?
The other one says basically the opposite.
It gives us the arrow in the opposite direction. It says, so let's think about the difference here. Our first principle tells us if you start from already knowing numerical identities, then you can get out property claims. If you know that Kent is identical to Superman, and you know that, say, Kent is a reporter, you can derive the fact that Superman is a reporter. From identity to properties. Our second one, the identity of indiscernibles, says, hey, if you discover that two things share all their properties, then you can conclude they are numerically identical. We've got a bunch of questions here, so yeah.
I don't really get the F.
Good. So in this case, one of the things to express this, we need to have a quantifier that quantifies over predicates. So this says, for every F, for every predicate, if A and B satisfy the predicates together, then they're identical. Or if they're identical, then they satisfy all and only the same predicates.
So basically what it also says is the identity of indiscernibles, basically saying, well, if they are equal, they have to be equal for them to have the same properties, but you're not proving anything by doing that. You can only prove that they are equal by them sharing the same properties. Is that true, or am I?
So our top one, right? So we have this is indiscernibility of identicals. This is in id. It tells us if identical, if you know you've got the same thing with two names in it, then it doesn't matter which name you use, the same property claims, the same predicates are going to be true. Our second one, it says if you work out that these two apparently distinct things satisfy all the same predicates, have all the same properties, you can conclude that in fact you don't have two objects, you've only got one. Numerical identity follows from qualitative identity. Or, the other one, qualitative identity follows from numerical. Yeah.
But then for the second one, you need an endless list of
Predicates.
because
Yeah.
for
We're going to come to that.
otherwise you have likes philosophy, like that TV show, like that food. Yeah, that can be more persons.
We're going to come to that, right? Yes.
For example, based on this identity of discernible, it will say, for example, if we take these two tables, okay, maybe if we ignore the sticker, that they are really, really similar, these both tables. Based on the identity of discernible, they will be considered the same
Yeah.
thing.
Yeah. So to use the other example, right, to come back to my type token, right, if these two tokens, if we genuinely think they're maximally qualitatively identical, that is, they share all and only the same properties, we don't have two tokens anymore. We've only got one. So again, so the identity of indiscernibles, the principle right here, hidden, this is one that's very frequently debated. It's super handy. If it was true, it would be awesome, because then we would have ways to settle questions about identity. Because we could just see, right? Do they have all the same properties? If they do, cool, then we know they're identical. Individuation becomes easier. And in fact, there's good reasons to think that this principle, that indiscernibility entails identity, is false. So this is what Black's article is about, the reading for today. So Black's article is a debate, it's a dialogue between someone called A, who's defending this principle, and B, who's generating counterexamples. Notably, you can also think of to come back to the question about the difference between these. Think about what you would need to show to make this one false. To make it false, what you need is two objects that have all the same properties, yet still are two, that they are not numerically identical. So Black's whole, or B's argument in Black's article is to generate some examples of that. Qualitatively indiscernible, numerically distinct. So let's talk about how the argument goes. Please.
Doesn't properties include like location?
Good. So this is one of the things that he talks about. Yeah. So good. Right? Because that's an easy way that these are qualitatively distinct, right? One of them's over here, one of them's over there. We'll come back to it. Okay. So we start off with A in Black's article, giving an argument for why this principle must be true. And A's first argument is really, really, really simple. And this comes back to your question of which properties get included. Right? He says, cool, just use identity properties. Use is identical to A. Anything that has the property is identical to A has to be identical to A. That's what the property fucking says. So if that's one of the properties that gets it put in here, then this is trivial. Because our two objects will both have the property of being identical to A, and hence they turn out to be numerically 1. It is cheap and dirty. Do you see it?
Yeah, I see, but how do I see it in like the
Good.
physical world then?
So that's not really there's a question about, cool, how would we test this,
okay.
right? But we're just thinking purely logically, is there any way to show that this principle is false? Probably. No, B replies, yeah, okay, cool, this is too cheap. This is too cheap because this just assumes what you're trying to prove. Yeah. Cool. So, right, remember, A here is trying to defend this position, give you an argument for it. And here's the argument. If you take a property like being identical to object A, right? What object will have that property? Well, anything that has it is going to stand in the identity relation to A, because that's just what it is to have a property. So when we think about maximum qualitative similarity, if you include the properties like being identical to A, this principle becomes trivial. Because it's basically saying, hey, anything that is A is A. Cool. But notably, this just presupposes this principle. It uses the principle, which is what it's trying to prove. So this is not a good way. And similarly, A says, okay, fine. You don't like identity claims. Let's use distinctness. Take the property of is not identical to A. Well, that's a property that A isn't going to have, but B will. And this is the same fucking thing, just in the other way around, right? This is just as cheap. So this is just assuming what we need to prove, not proving what we want to. Yeah.
I don't get how.
So remember, right, the debate here. The question is there any kind of counterexample to this condition? Is there any way to make the antecedent true and the consequent false? A wants to say no, B wants to say yeah. A's initial arguments are basically, oh look, there's no way to do this because when you think about the stuff that you can feed in, what properties to consider, well, there's some properties that are going to make this guaranteed. Properties like being identical to A or being distinct from A. Because anything that has the property of being identical to A, well, is numerically identical to it, trivial. Similarly, anything that has the property of being distinct from, i.e. not identical to, well, it ain't going to be A. So these ones will give us this on the cheap.
Like, if you do that, the antecedent will be false.
Antecedent will be true, but the consequent has to be true. Because it will be basically like, it is that claim. That's with the identity property. Alternatively, it is this claim. Because remember, the left-hand side, the antecedent to the conditional, says, I hold for every property. And if the properties that get fed in here have to include ones like this, there's no way to make this false for every property, because it has to include these ones. Okay, think about it this way. These two, right? We have location. Let's put that aside. We have the fact that they're both A. They're both instances of the same letter. Cool. But we also know they're different because this one has the property of being identical to, I don't know, let's call it 1. And this one does not have that property. In fact, it has the property of not being identical to object 1 because it's identical to object 2. That's all this first initial move is.
I don't get how that appears in the formula.
Has to be for every property. So if you include in every property these ones, it's guaranteed.
But basically, for every identity, there will be some that will be true.
Yeah. And all we need to do to make this true is to lock on to just those ones. The rest are just wash out. These are the ones that are doing the heavy lifting. It's not a good argument. So I think you're giving it too much weight. Right? It's basically saying, hey, I can give you this super cheap. Ha-ha! And then they both kind of agree like, yeah, that's too cheap. This is cheating. Right? This is assuming what we want to prove. So then they say, okay, let's not cheat. If we're not going to cheat, we have to come back to the question of what properties are going to be included here. And the thought is, well, we can't include any properties that are identity properties. That is, you can't include any non-qualitative ones. More specifically, you can't include properties that essentially involve reference to particular individuals. So here's a property. Being at the foot of Mount Fuji. This property makes reference to a particular individual, Mount Fuji. So this isn't a purely qualitative property. Because to understand this, to figure out what property this is, you need to know who this is already. Being the child of, God, I forgot Socrates' parents. We'll use my mom and dad. Joe and Cindy. Being the child of Joe and Cindy. That's a non-qualitative property because it refers to two particular individuals. So the restriction here, to make sure that we're not going to get this on the cheap, is that whatever properties are going to go in here, they cannot mention specific individuals. No names can be in the predicates. No is taller than Steve. You could have things like is 2 meters tall, but you can't have is taller than Peter Crouch or is faster than Messi, because that essentially invokes a particular individual, and that will take us right back to, oh, this is cheating.
So that's what you said about just qualitative.
So pure qualitative, do not make reference to anybody in particular. They all drop out. It's just going to be things like, is red, is a table, is by a mountain. These kinds of things. Is a sphere, is made of steel. Right? Has a parent of this type, has a parent of that type. As long as there's no names, any of the properties, we're good. Because if there are any names, we're right back to, oh, this is too cheap.
So empty predicates?
Empty predicates are cool, right? I mean, that's no problem, as long as the empty predicates do not reference any names. But of course, there's no problem with unempty ones, right? Is a table. That's fine. Yeah.
Just still can say that something is identical. Right?
No. So what you could say is self-identical, but that's just a property that everything has. That's not going to help. Because that's just standing in the identity relation to itself. That's this.
If you want to find out something that has a property that is the same, but then this is too vague, right? Because then you have to say at the north side of Mount Fuji.
Well, you couldn't even say that, right? That's not a purely qualitative property, because that makes a reference to Mount Fuji. You could say, is to the north of a mountain, because that drops out any talk of this mountain. No names. No names. It's got to be the kind of thing that if we wanted to be pure descriptivists, we could get away with.
Parents, your parents can.
Parents has parents,
Yeah.
but we couldn't have Joe and Cindy, because that's using names.
So it's identical to the need cannot be a predicate. It can only be an identity. The same way you could say like Nathan is in love with Danny should be a two-place predicate, not a single predicate.
That's the idea.
Okay.
Doesn't turns out that if something is based on this rule identical, then it's also self-identical
Yeah, that's good. So self-identity is going to follow, But it-
naturally, like logically.
because everything is self-identical. That's no problem. But because this is something that everything has, it's not really going to be helpful for our identity of indiscernibles. Okay, so they restrict it down to certain kinds of properties. All right. So then B comes along and says, all right, I can give you some counterexamples with this restriction in place. B is the one who wants this to be false. And here's the kind of build-up. Right? So we're going to give a thought experiment, and it's going to be one where the antecedent's true and the consequent is false. Here's the argument. Here's Black's initial scenario. Really weird, but it works. At least it seems to. Suppose that all there was in the universe were these two identical spheres. Right? And these two identical spheres are made of chemically pure iron. Notably, iron has a particular chemical structure which mirrors itself, so it's not asymmetric. They're made of chemically pure iron. They both have a diameter of 1 mile, so they're the same size. They're the exact same temperature. They're the exact same color. They have the same amount of rust on them in the same places, mirrored in the right kind of way. So you have these two giant spheres. That's all there is in the world. Well, okay, suppose the universe contains these two perfectly symmetric iron spheres, 2 miles apart, and they have all the same intrinsic relational properties. There's two of them, but they're indiscernible. That is, every predicate that you can think that's purely qualitative, they share. Iron, distance apart, the sphere, diameter, color, blah, 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 blah. But there's two of them. One's over here, one's over here. So, antecedent true, consequent false. So much the worse for the principle.
Because there are two.
Because there are two. Because there are two. So again, the argument is, suppose there are these two spheres, perfectly symmetric, made of iron, they're 2 miles apart, same color, blah, blah, blah. This seems possible. They're qualitatively indiscernible once we eliminate the kind of identity predicates. But there's two of them. So principle's false. Antecedent's true, consequent is false. Yeah.
stating that they are in different places in the universe, doesn't that give you a predicate?
This comes back to your man. Nice. So one thing we might challenge this with is, let's think about location. Let's think about location properties. One of them's over here. One of them's over here. Surely that gives us a difference. Surely that gives us a difference. Cool. Do we see how that at least seems to raise a problem? That suggests that premise 2 is false, because location properties seem to be a point of difference. We might say, okay, look, they have different relations. One of them has a relation of being 2 miles away from A. One of them has 2 miles from B. Of course, this is just an identity case. But we might also appeal to location. This is the suggestion we just had. They have different spatial locations. One of them's over here, and one of them's over here. B's reply is, that don't help. Right? And it don't help because this begs the question. Think about the reason you would say that they're in different places. Why would you say they're in different places? Well, unless you have a principle that tells you when places are different, which looks like it ain't going to be this, we're right back on the same problem. Put another way, why do you think that here and there are different locations? Easy answer, they've got different shit in them. But that's just what I was trying to show you. So if that's what you mean, I win.
This is very, very abstract.
It is, but again, think about the idea, right? The idea is we have this weird world with just these two objects. And the two objects are mirrored, effectively. They're 2 miles apart. And an initial move, a very plausible move, is they're in different places. But then the challenge is, why think they're in different places? But how do you know that there and there are different?
Because the first there refers to one specific temporal, but the special object, and the other there refers to another special.
But that is already presupposing that they're distinct objects. So that's to say, oh, they're distinct, so they must be different. So that's why.
Okay, but I am presupposing. Oh, but that's there.
That's basically what the reply is here, right? Appealing to location requires you have a way to discern location. But discerning location seems to require already being able to discern the difference in the objects. Yeah.
Would you just say that because there is no, let's say, third party to hold them relative to, their location is irrelevant?
Yeah, basically. If we had a third object that could kind of step in and be like, facing this way, it's over there, and it's over there. But of course, that's to change the case.
So otherwise, it would just have to be relative to the other, which means it would be an identity issue for two-phase.
That's the problem. Right? That's the problem. To say they are in different places looks to already presuppose that these are different objects, but then we're right back into the thing that you're trying to prove. Right? Yeah.
It's the same problem as with the falling tree that makes sound, and if there is nobody that can hear the sound, it doesn't make
In some sense, right?
Yeah.
But in this case, the reasoning hinges on the fact that the individuation of spaces seems to entail or require already presupposing the spheres are different. Again, it worked here because we can see them, and there's a whole bunch of other things for us to be related to. Right? Do we see the kind of idea? Yeah.
Well, what if the two spheres can interact with each other or see each other?
Good, that's totally fine. Because whenever one does to one, the other does it back.
It's like a mirror.
Yeah. In fact, that's the next version of it. Like, cool, right? I don't think this works. But we can make it even worse. And we can make it even worse by basically having a perfect mirrored world. Add more shit. I don't care. As long as space is such that there is some line upon which it is symmetrical, then my puzzle continues. Because if there is a line of mirroring, then I can keep going. Whenever you think you're talking about this one up here, just as equally applies to the one down here. But of course, they are mirrored, so there are two, but purely qualitatively, there's no discerning the two. So, go ahead.
Well, no, yeah. My mind is saying Emily.
404.
Yeah.
You're telling me there are two spheres, and now if it's supposed to be mirrored, then it's one thing. But then we are away from the two spheres, right?
So importantly, if it's mirrored, what we don't mean here is that it's literally like there's a giant global mirror, it's just a reflection. We mean that whenever there's one thing over here, there's going to be another thing qualitatively identical to it.
But
And
then
this,
there are still two A's, right?
there are still two. But for every qualitative property, they are the same.
And then it's A is B.
Then they are, but they are not identical.
Oh,
Because the whole point is to say, this is true, this is false.
yeah.
And the mirror is now going to give us a way to do that. Says this.
What if there's a different time zone? So one is in slightly in the past, and the other one is
Good.
10 minutes later or something.
Good. So one thing that's kind of lurking in the background here, and this is interesting, actually, I passed over it, but this is something Black talks about, is this sort of different location objection actually only really works if you buy into the Newtonian conception of space. If you have a relativistic conception of space, then you couldn't even get this distinction, this kind of objection going.
So, relativity.
Relativity works wonderfully because that favors black. That favors the possibility of qualitative indiscernibility, but non-identity. So the last kind of version, please.
How is it that the sides are perfectly symmetrical, but they're not quantitatively identical? Because then it's similarity to the maps, right? And they are exactly similar.
Hold that thought. We'll come back to it. So, again, so they've started off with the two spheres, and by stipulation, they're supposed to be qualitatively identical, but numerically distinct. And the challenge is to explain it away. First thought, location will do it. Black says, no, because difference in location is driven by difference in identity, and that's presupposing what you're trying to say is the case. So then he says, all right, but I'll make it worse. Let's suppose that however many things there are, we have a kind of plane of duplication. Well, that would make it even worse. This makes it kind of realistic. Because whatever's happening in this bit of the universe, let's suppose there's a line going across all of existence, and suitable ways, mutatis mutandis on the other side of the line, the same shit's happening over there. He says, cool. Well, there's a problem with mirrors. They work really well for things like spheres. But there's a lot of shapes where mirror images don't give you qualitative identity. Gloves is a good case. If you mirror this, you get something that's qualitatively distinct. Right? It comes in backwards. So there would be ways then maybe to still do some demarcation with the mirroring. So we go to the craziest version. And I just want to raise it. The craziest version says, all right, the problem here is the way we were thinking about mirroring. So let's do radial symmetry. Don't stress. I just want to kind of mention how this goes, right? So the radial symmetry is the basic idea. You guys will be familiar with this concept even if you've not heard it in these terms. Look at the mandala. take any kind of slice of the mandala, right? So go from the point in to the other point. Note that every given slice as you go around is going to be effectively that, just suitably rotated around the center point. Do we see the idea? So radial symmetry is effectively, instead of having a line mirror, you have a point that everything is rotationally mirrored around. And the reason to go with this is this avoids any problem about handedness. Right? To go back a slide, this doesn't work very well if you just have a flat mirror. You run into these problems. If the universe is radially symmetric, don't come up. Because all you do is rotate around the center point, mirroring around the center point. The really cool thing is, space could physically be shaped like this. This is a physical possibility.
Really, really?
Really, really. So you could have a center point and the whole of the cosmos is radially symmetric around that point.
I'm lost inside.
Don't worry. So the important thing,
There is a center.
there is a center.
And I
So the important thing to come through here, right? Note there's these additional versions. There's the mirror, there's the radial symmetric version. But this is really the core. This is the core argument from Black. It seems like we can have a case, however detailed or nuanced we can get with the flipping locations or radial symmetry or whatever. It seems we can have a case with at least two objects that share all of their purely qualitative properties, but are not numerically identical. Because they're just two spheres floating in the void, because there's a slew of them and they're all radially symmetric around some center point in space, because there's a giant radial, a kind of mirror plane cutting across space and they're duplicated. We don't care how. Okay. So, if Black's right, then the identity of indiscernibles fails. But A has a reply, and A's reply is exactly the one that you gave a second ago. The reply is, right, this kind of mirroring is super cool and fun, but also your description of this mirrored or twinned or radially symmetric universe is the exact same description we would give for one that only has one instance of each object. Because all your description would ever be is of a slice. And then you would say, oh, and the slice is then repeated and repeated and repeated and repeated. But there's no reason to think that actually repeated doesn't just mean you're talking about the same thing again and again and again and again. Or put another way, think of the initial just case with the two spheres. Well, that might just be a weird way of talking about one sphere standing in a really fucking small universe. Just looking at itself. So the upshot here is that there seems to be a really hard break. If you think that Black's description of there are two, and that's key to what's going on in the description, makes sense, then we have a counterexample to the identity of indiscernibles. But if you think that that could just be another way of redescribing the same stuff again, then we have a way of defending the principle further. So the upshot is, if we accept Black's thought experiments, so much the worse for the principle. And we have good reasons to think they work, right? The argument is very clear and straightforward. But of course, we have some responses. The response could be, you're just redescribing the same thing using multiple names. So this is a very weird case. But I think it highlights something quite cool. Which is, again, this idea that there's a connection between identity and similarity. qualitative and numerical identity are related. But how? This one seems trivial. If they're identical, then you can just do the substitution. They share properties. This one looks harder. And it looks harder because it seems like we can construct, at least if we follow Black, these sorts of scenarios where things share all of their qualitative properties but remain distinct. Okay. How we feeling? Broken? Yeah. No, it's okay, it's okay. So why don't we'll take a 10-minute break, come back 5 after, and we'll do the last little bit here. Cool.